Okay, ladies and gentlemen, I'm going to go over here some very classic integral questions for you um, and derive a formula that you can memorize and use. They're that classic and they will show up over and over again. This is the integral of tangent and the integral of cotangent. So notice these functions are not inverse trig functions. You did integration in Calculus 1 with some trig functions, integral sines and cosines, those kinds of things. But now in Calculus 2, you can integrate tangent and cotangent. So let me show you how you do that. So the first question we're going to look at this morning is we're going to integrate tangent here. And how you do that is you replace tangent with the sine over cosine identity. So tangent's going to be written as sine over cosine. Now, just to do a really brief compare and contrast that to the eventual integration of cotangent that we will work with. And you're going to do the same idea, but you replace cotangent with its identity of cosine over sine here. So we're just going to compare and contrast these two very classic questions. And let's try to integrate these, okay? So this is what we're saying. This is equivalent to what you see here, and this one will be equivalent to this. Now, the key here is to use u substitution. So we're going to use u sub on both. What u is going to be different for each integral. So in the first case, our u will be cosine. So we're going to let u here be cosine. And in the second case here, just to kind of remark, u is going to be sine, but I'm going to go away from this one. For number 2, we'll focus on u sub separately now. So, okay, so this is a different question. We're going to focus on these separately. So let's try the first one, the integration of tangent now. Okay, and it's really u substitution. Now remember, du dx, that's the derivative of cosine. And the derivative of cosine is minus sine. So du dx is minus sine. So remember, in the process of u sub, we have to solve for dx. I remind people that you just simply create a proportion solving for dx. And when you do that, of course, you're going to get du is minus sine dx. And dividing both sides by minus sine, you'll end up with your dx being du over minus sine. Okay. So here you go. And now we're ready to substitute. So remember these two key ideas. We have u, and now we have dx. So ladies and gentlemen, let's do that. We have the integral of sine over u times du over minus sine x. And notice that the signs cancel. Be careful here. You have that minus sign there. Bring that minus sign out. It's a constant. So you have the integral here. Negative integral 1 over u du. Now, take a look at that. That's going to be the process that we use here. And now I make the claim, go back here. You guys have done this kind of work already. You guys can integrate this. We know that integral. This is the natural log, absolute value of u plus c. So notice this here. We have that memorized. And putting this all together, just simply replace u now with what it is. So you might say, what was u to begin with? Well, u is over here. U is cosine x. So, ladies and gentlemen, we're going to use that. U is cosine x. Okay. And so our final answer is going to be minus natural log absolute value of cosine plus c. So this is our answer. And I guess I'm going to do something here. I'm going to put that in black. Minus natural log absolute value of cosine plus c. And ladies and gentlemen, there you go. That's what you got. Now, you might look at some books here and they'll say, well, they're going to use properties of logs now with the constant that's in front of the natural log, this -1. Here's what I'm going to remark, that negative is -1 here. And we have the power rule for logs. So we're going to be able to move the power here, because if we think of it, we say, hey, that power belongs to the argument, the inside function for the natural log. So this is really what we see here. That -1 now is on top here. That's the power rule for natural logs. And then all together now, using a little bit of algebra, if you will, right in here, just remember that any base to the -1 power is 1 over the base to the +1 power, which is just going to be 1 over b using a little algebra. So you end up with the natural log here of 1 over the absolute value of cosine plus c. Now, you can think of this 1, just so you guys know, as the absolute value of 1. So you have the absolute value of 1, because that's what it's equivalent to, is the absolute value of this cosine. So let me get this here. Now, working on the algebra and then using properties of absolute value. Remember, if you ever have the absolute value of, well, I'll write it this way here. If you ever have the absolute value of a quotient, that's quotient of absolute values. And so you end up with the natural log here of the absolute value of 1 over cosine plus c. And I'm going to remind you that this is a reciprocal identity, that 1 over cosine is our secant. So altogether, this very famous demonstration now, that when you integrate tangent, let me write it this way here, that the formula you get for integrating tangent is the natural log absolute value of secant plus c. Now, I'm going to really recommend you memorize this, because this shows up a lot. This integral shows up a lot. So in the Calculus 2 course, just memorize that one, okay? And now you're free to use it. And you might say, okay, how do we use that? Well, I put a note here. We're going to go through this. Don't forget, we're going to do cotangent as well. But I want to kind of talk a little bit about this integral here. If I said to you, the benefits of memorizing that particular formula is that when they give you another question to do like this, what you can do is write the u sub version that we've been doing. Every time we have a formula, we have a u sub version now. So all of our integral formulas, we have u sub because this is going to show up. So here's our u sub. And a question how we can apply u sub. So let's see what I'm talking about here. All right, so here's the u sub, and in the context of another example that I labeled just as a note, just notice this as an example, we can apply u sub here. So the benefits, again, of working with all of those u sub questions I've given you guys here is that we're going to try u sub here. We're going to let u be 10x now. And when u is 10x, of course, we go through the u sub process. We differentiate this function. And that is going to be 10. So, ladies and gentlemen, du dx is 10 over 1. And we can now solve for dx. So dx now becomes, if we solve for dx, du over 10. So, ladies and gentlemen, there you go. Let's apply our substitution now. So when you integrate tangent u, dx is du over 10. And what we can do is pull out again the constant. And this becomes 1/10 integral tangent u du. So at this point, let's go back and remember, do we have a u sub formula for this? Yes, we do. It's the natural log absolute value of secant of u plus c. So having that in your memory banks is very helpful. And u now, don't ever forget, our u value is 10x. So let's let u be 10x because that's what it is. Replace this with a 10x. And so, ladies and gentlemen, you have 1/10 natural log absolute value of secant 10x plus c. All right, there we go. So that's kind of, again, the benefits of having that integration of tangent formula in your memory so that you can actually just apply it really quick in a u sub setting like that. Okay, so I just want to kind of remark about that example. U sub. And I guess I do have another note here. If they give you this tangent 1/2 x, I mean, I guess I want to give you some variations. So forgive me for that. I'm going to give you, I mean, even though at this point I should say you guys should be these experts, right, in U sub, right? In this case, let's try it again here. Let U. We can always use more practice, I guess. U is 1/2 x. Let's see how U sub is applied to this formula here. Du dx will be d dx of 1/2 x, which is really what? 1/2. So du dx 1/2. You can cross multiply. And what that gives you now is dx is 2 du. Okay? So don't forget, we got to solve for dx, and it looks like we just did just by cross multiplying. So here's our dx, which we'll replace here with our u sub. And now, ladies and gentlemen, we end up with the integral of tangent of u times 2 du. So you can pull out your constant. And when you do, we get 2 integral tangent u du. Apply your u sub formula. So when you integrate tangent now, and you apply that formula, we pulled out the constant. So natural log, absolute value of secant of u plus c. So we get 2 natural log, absolute value of secant of u plus c. Our u, don't forget, was 1/2 x. So 2 natural log, absolute value of secant, 1/2 x plus c. So there's a variation again using that memorized formula here that we demonstrated to you for how to, we should say, integrate tangent, okay? Now, remember I said to you, we're going to try this other integral of cotangent as well, and then see how to apply that too. So let's actually bring it down. Okay, so here's the very famous integral of cotangent now. Okay, let's create that formula. Let's determine it. Determine the formula. Okay. So if we let u again be sine with the u sub process, that's what we're using. All right. We're going to get now the derivative of u with respect to x. We have to differentiate sine. And the derivative of sine is going to be cosine. So I will just do it this way. Du dx is cosine. So we're going to place that over 1, because remember, for u sub, we have to solve for dx. So using cross multiplication, we get du is cosine x dx. And then dividing both sides by cosine, we're going to get our du over cosine equals dx. So let's remember, this is what we're going to use, this dx here. Okay, so if we go back now to this question, here's what we'll have. You integrate cosine x over u, and you get dx, du over cosine. Remember, cosine cancels. And then you're going to be left again with 1 over u du. So we know what this equals, or we know what this is. This is the natural log absolute value of u plus c, which means this is the natural log of u being sine in this case now. So we replace this u with sine. I can write it down here. So we get natural log absolute value of sine plus c. So let me write this in black. And you get natural log absolute value of sine plus c. So, ladies and gentlemen, here is the very famous formula on the integral of cotangent. So once again, you will have a formula, an integral formula. We get the u sub free of charge. So I also recommend have this in your memory banks. Have that in your memory banks, ladies and gentlemen, and now you can use it for some various other kinds of examples, like if they want you to integrate cotangent. How about this one? So, we'll give you guys a few examples here of this as well. And I'm going to remind you, let's let u be what? 2 pi x. And we get du dx now is 2 pi x. And that derivative, we know, let's do it, is 2 pi. So your du dx becomes equal to 2 pi. We'll put that over 1 because, again, we're going to solve for dx. This is a proportion. So you end up getting du is 2 pi dx. Divide both sides by 2 pi, and you get du over 2 pi is dx. Okay, there's your dx. Now, see, let's look at this from afar, I guess, or take a look at what we're doing here. Okay, we're going to apply that u subversion. And now, ladies and gentlemen, this is what we end up with. The integral of cotangent u, and our dx, remember, is du over that 2 pi. You get to pull out your constant 2 pi. Okay, now you get to apply the formula you memorize. Remember, the integral of cotangent is natural log absolute value sine. So we get to replace this with natural log absolute value of sine. So I have 1 over 2 pi times that natural log absolute value of sine here. Okay. But we got to recall u being 2 pi x. So we're going to put that in. So, ladies and gentlemen, 1 over 2 pi, let's write this down in black again, our final answer. We got the constant 1 over 2 pi, natural log absolute value of sine 2 pi x plus c. All right. Because again, here's the U. So this is how you apply that formula. So you do want to memorize that. And it's not too bad now if you do it this way, ladies and gentlemen. It isn't too bad. Let's try another example of that formula we derived. And, and that'll be a good, I don't know, review or just a good sort of immersion in how to go about this process. Let's go to that other note I wrote down that we should try to do just for fun. And I'm going to bring that one down. And we're just going to go through the U sub process with this formula. And that's going to be a common theme that we'll see with these integral formulas for us. So ladies and gentlemen, let's try this out, okay? And right in here, this is our U. So U, we're going to say let U be 2/3 x, which means du dx is 2/3, okay? So let's see how that works now. Du dx, we create a proportion, cross multiply. So you end up with 3 du is 2 dx. Solving for du now, you get du is 2/3. Oops, solving for dx, I apologize. Solving for dx, we get 3 du over 2 equals our dx. So we now have the dx as well. So this is just plain old U sub. Okay? So you now have the integral of cotangent U, where the dx is really 3/2. Now, that's 3/2 du. So just pull out your constant of 3/2, and you end up with 3/2 integral cotangent U du. And so, ladies and gentlemen, integrate your cotangent. Don't really. You have the formula here, right? The U subversion, we went through the derivation. Natural log absolute value of sine of U plus C. All right, so we end up with 3/2 natural log absolute value sine of U plus C. Go back and recall that U was really going to be 2/3 x. So we're going to use that. Copy. Okay. And so here's the final answer. So I recommend these two formulas be placed into your memory banks, ladies and gentlemen, because as you guys can see now, if you are familiar with the U sub process, and by now you should be, then that makes everything a lot easier. And that's going to be a theme of the course by using and deriving these formulas, as you guys will see. So thank you for your time, and I'll send this to you.